Hi everybody, welcome back. So we're still going through dimensions this time. And we're going to be jumping to two other dimensions, which are also probably not that well understood. First off is time. It describes time. Soon, long, short, you know the words. Now, what is time? Where do we get it? Well, yes, there is chronology. We know that something happens in the past. But you might have also heard about the whole time dilation thing. Like you move fast, time passes slower for you, and you're like your mind blown. What? How does that work? Well, the reason we believe that and know that is because light, the speed of light, is a constant. Now you're like, okay, cool, but the relative speed of light is also a constant. What I mean by this is, like, if you're driving on the highway and you look at the person in the lane next to you, if they're going the same speed as you, then even though both of you are moving maybe 60, 70 miles per hour, it looks like they're not moving, just like relative to everything else. Relative to you, their speed is 0. Now, if they're faster than you, their speed is a little bit higher than yours, but you're both going 70 miles per hour relative to the ground. Relative to each other, it looks like you're not moving at all. Light's not that way. No matter how fast you go, light will always be going the same velocity compared to you. When you measure its velocity, it will still be going at that amazingly fast speed. And the only way that's possible is if time is moving more slowly for you. So you're going super, super fast, but time is moving more slowly, and so therefore light still has the same velocity. Okay. So I know that's kind of a crazy thing, but you don't have to understand that to pass this class, or even to pass most of your classes. That's like in quantum physics. I still remember the day I saw the equation for it. I'm like, oh, there's time dilation. That's terrifying. We found it finally. But how is time measured? It's measured in seconds. And luckily, all systems use the second, minutes, hours. Finally, there's some agreement on that. If you want to know what the second is, it's technically based on the radiation of a cesium atom. There's a certain number of periods, which you don't really need to know. There is a way they measure it. A second is defined by a certain quantity. Okay. Lastly, temperature. Now you notice that there's this strange symbol that's a theta for temperature. It's only for when we get to dimensional analysis. Even if we do, I might not do it. But we use thetas because T is for time. We can't use T again for temperature. And I say, how much is it moving on a small scale? Because temperature is actually technically a measure of kinetic energy. You're like, kinetic. Isn't that like moving? It is. Yes, kinetic energy is all about moving. And we're like, well, so if I'm running, I'm hotter than if I'm slowing, slow? I get where you're going with that. But I'm talking about microscopic kinetic energy. I'm talking about the vibration of the molecules in your body, the atoms in your body. Those vibrate constantly. When they vibrate too much, they react, they break apart, they burn. You don't want that. So temperature is measuring that kinetic energy of how much you on a microscopic scale are vibrating, are rotating or spinning up and down. I'm talking about the atoms and molecules, not like you got tremors in your hand. So that's what temperature is. It's actually a measure of that kinetic energy. Okay, so metric uses a Kelvin. You're like, wait, what about Celsius? I'm not too keen on metric, but I've heard of Celsius before. That is a temperature scale, but it's not the actual base unit of temperature. The reason is because Kelvin starts at 0. There is nothing less than 0 Kelvin. There is something less than 0 Celsius, just like there's something less than 0 Fahrenheit. And a Kelvin is 1/100th of the temperature change required to boil water from being frozen in standard temperature and pressure. The USCS and AES systems, once again, they use the same thing. It's called Rankine. And you're like, wait a second, where's Fahrenheit? I know Fahrenheit. We've used Fahrenheit before. But just like before, Fahrenheit is it's a relative scale. It means 0 is not the lowest temperature you can have. You can go lower than 0 Fahrenheit. It's terrifying and it's cold. I've been there. Michigan is a cold place. But it's not a 0-based scale. 0 Rankine is the lowest you can go. Okay, now, in most cases, you're like, well, Celsius makes so much more sense. Kelvin makes so much more sense. Why is Fahrenheit so weird? Like if you look at it, I think boiling is like 230 Fahrenheit and freezing is 32. It doesn't make any sense. That's not. I like this whole metric system. It goes from 0 to 100. But don't knock Fahrenheit too much, because Fahrenheit, I'm talking about Fahrenheit here, not Rankine, was originally based where 0 was the coldest temperature that people usually see, which is when seawater freezes. 0 Fahrenheit is roughly where it's where seawater will freeze, and it's also the coldest temperature that most people see. And 100 Fahrenheit was originally what they thought body temperature was. It's just as they got more accurate, they realized that they were off, that our body temperature was actually 98.6, and actually it's technically dropping. So they're not crazy, it's just, it was based on different ideas. They were just trying to get the full range of temperature between 0 to 100 that most people would see in their lives. Now, if you go to Antarctica, you can get colder. If you go to some parts of the Sahara Desert, you're going to get much hotter. But most people, 0 to 100 is the most they're going to see. So with that, we'll stop here. I'll see you all next time. Bye-bye.